Welcome to our weekly Thursday afternoon Colloquium series. We have former students. What's that again?
I think she means to.
She turn it on.
Yeah, turn it on.
Is it on now? No, green light. Okay. Caleb Baker is one of our own students. He graduated in 2017. He did his Ph.D. with Professor Maloney here, and also Jason Jones. And I think he had some work done with neurocortex as well. Maybe
Mirrors are theories. We have beef. That's not true. That's not true. I love Miro. Miro is awesome.
So he took my class, electrodynamics, and he came to my office very many times. And he called himself a rad dude. He never understood what it is. Now, it turns out something that goes back to the 1970s, before I was born.
Right.
And in simple terms, it means a cool dude. But that's what he thinks of himself.
Am I wrong though?
What?
Am I wrong though?
You are correct. Now, he is a group supervisor at NASA's Jet Propulsion Lab. And he specialized, when he was a student here, he specialized in ultrafast semiconductor laser design and engineering since joining JPL. He has worked on a variety of spaceflight optical systems, including laser metrology, Psyche's deep space optical communication terminal. Psyche is the name of an
asteroid and a JPL project to go to the asteroid.
An asteroid and a JPL project to go to the asteroid. And on CGI, he's going to talk about that. His major roles in CGI were optical system engineer for the instruments Deformable Mirrors, and later he was manager of the simulated star source used during ground-based testing of the coronagraph. Please take the mic.
Okay, so thank you everybody. Thank you for the invite. Thank you, Masood, for the introduction. Since Masood punked me in the introduction, I'm obligated to tell a story. I love instruction and teaching, mentoring, tutoring, and while I was here at OpSci, I was particularly a fan of our own Brian Anderson's teaching style. So one day I went up to Brian's office and we were talking about teaching philosophies, and Brian was explaining his to me and how he considers himself to be sort of a motivator and allowing the students to teach themselves. And Masood walked in while we were having this conversation, and I asked Masood what his teaching philosophy was, and he said, "When I am in the classroom, I am God and all the students must listen to me." Okay, again, thank you all for coming. I am very excited to give this presentation because I remember being here and coming to these every week, and it is an honor to be up at the front giving one. There are less shocked faces from the professors in the room than I thought there would be at seeing me up here, which is a good sign. So I wanted to give you all a walkthrough of the Roman coronagraph. And to start with, there's a heavy disclaimer on top of this that I am giving the presentation, but an instrument like this takes hundreds of people to put together. So many that I started writing all of the names out on a PowerPoint slide and gave up. So to give you a better shot or better intuition, here's our group photo, not inclusive, so a lot of people miss this, including me, of the chronograph packed up for delivery out to Goddard. This happened in May of this year. And here's another shot. We had everybody sign a flag, or as many people as we could get, and we taped it to the outer ESD protective material with Kapton to prove that we are a NASA center. So an additional funny addendum to this disclaimer is that I am not actually a coronagrapher. I am laser development, I'm a technology development type of person. I got wrapped into the chronograph by working on the DMs But I figured it would be more interesting to everyone if I came and talked about the coronagraph as a whole, instead of just blathering on about DMs for 45 minutes. So what I would like to do instead is walk through the Roman mission, what the goal of the observatory is. I'll mention the primary science instrument on it. We'll go through, what is a coronagraph? What's the optical layout? We'll talk through how we assembled it and go through, cover the performance results from our thermal vac test. A lot of the information in this presentation is gathered together from a series of talks that I and a lot of the other subject matter experts on CGI gave at Caltech. And so if you go to this YouTube channel right here, it's Caltech IPAC. There is a series of like 20 to 30-minute talks from all of the people who are actually experts in the various domains of the coronagraph, and it's very interesting and very deep dive technically. Okay, so let's start with the overall mission and instrument. So the Nancy Grace Roman Space Telescope is sort of the latest in a long heritage of NASA astrophysics space-based telescopes, dating all the way back to Hubble and covering a lot, including, of course, James Webb, which is very famous for taking a long time, costing a lot of money, and then doing amazing science out of it. Roman is set to launch at no later than 2026, and it's being followed. We're in the early development stages of the Habitable Worlds Observatory, which will follow on, and I'll sort of point that out, how HabWorld is set apart from Roman later. This is a nice little CAD shot of Roman. It's a 2.4 meter primary with a stubby little form factor, and then the primary science instrument fits in there, and Roman or CGI slots in there. The overall observatory and the mission is managed by Goddard. It's planned to get launched out to L2. And the primary science instrument is a wide field imager. And to give you an idea of just how wide field this little tiny square is, the Hubble field of view, and this whole thing is the Roman field of view. Again, wide field instrument is managed by Goddard, so ooh. No, Goddard is great, and they do great stuff. I love this shot of the wide field imager detector array out in a Goddard clean room, because it's just a real beautiful thing to see. CGI is a high contrast imaging system. It is meant to block out starlight and detect exoplanets. It is a risk class D mission, which in NASA terms, that is the move fast and break things type class of project. It also cost around $450 million, which puts a bit of a damper on the break stuff part of that description. And it was managed and implemented by us. Goddard contributed a lot to it as well. We had industry and international partners, including people from JAXA and ESA. It'll be the first coronagraph in space that uses active wavefront sensing and control. A lot of other systems, including Hubble, have coronagraphs on them. They don't include the high order wavefront sensing and control aspect of it. They don't have active deformable mirrors. Here's a shot of the instrument. It is a beast. There are 66 optical elements, 25 inside the beam at any given time. 2 EMCCD cameras as 2 40 by 48 deformable mirrors with 3,200 individually controlled actuators. It has 6 precision XY mechanisms to align masks and filters and so forth. It has 49 electronic slices and 9 unique FPGA designs, to over 260,000 lines of code, and that does not include the high order wavefront sensing and control, which is done ground in the loop because it would be too large and cost too much to fly. So it is large. There is a nice shot of the real thing. The optics bench sits on top, and then this large wrapped package down at the bottom is all of the electronics. To give you a sense of size and scale, it is roughly the size and, interestingly, the shape of about a grand piano, which our deputy INT lead loved to point out, because he'd like to point out that Johannes Brahms was never certified for a cleaner. So shout outs to Charlie. He insisted I include this chart. Okay, the Roman chronograph's goal is, if you look at this plot here, in separation of exoplanets from their host star versus the flux ratio of the planet to the host star. Ground-based systems, current space flight chronographs sit up here on this little diagonal. They can see stuff that's either really bright or really far away from the star. And Earth is sitting way down here tight into the star and really dim. That's true of most rocky planets that you have to see in with reflected starlight. Roman chronograph is not designed to get us to Earth. That is a huge technical challenge that is being tackled by the Habitable Worlds Observatory. And the Roman chronograph is the first step towards that. Our requirement actually sits just slightly underneath the performance floors of all of the other systems, but our predicted and goal performance sits about halfway between them, and we're really targeting this, we're really crossing our fingers, I guess I should say, for an exo-Jupiter. That's if we can image an exo-Jupiter, everyone will be extremely happy. Okay, I felt like this would be the best time to show you this list of acronyms. Good luck. So I will do my best to call out the actual names instead of relying on the acronyms, but I couldn't help but poke fun at that. Okay, so the optical subsystem. Everyone here is optics, so that's what we're going to focus on. It is quite complex. The beam comes in to the fast steering mirror from the Roman Observatory, and then it goes through some OAP relays, a focus control mechanism, the two DMs here, and then back through the bench, gets picked off for the low order wavefront sensing and control portion, through some other some other masks and filters to the science camera. And we'll go step through each of those as we go along. Here again is another shot of that. Beam path comes in from the observatory, goes this way through the DMs, and then this way back through the system to the science camera. You can see here, my favorite part is that we gold-plated our camera electronics and our DMs for thermal regulation, but also that is the most Gucci aesthetic thing that we could think of, so put that on the bench. So real quick, I talk about how complex this is, but if you went, for example, to an EUV lithography center, or even maybe the quantum optics labs here at U of A, they might scoff a little bit at 25 elements being complex, but to defend our credibility, you don't often do this to lab-based systems. Yeah, on a vibration table, simulating what it's like to be fired in based on the back of the rocket. Yeah, we're in California. Yes. Typically, what's happening here in science on one axis, you have to do all three axes, you have to translate. So your line effect. You can imagine if you thought 5 that having to do this here, then maintain the line effect. So what is a chronograph? If you are a high contrast imager, please bear with me because you already know a lot of what's going to happen in like the next 20 slides or so. But for everyone who's not a high contrast imager, you still already have an intuition for what a chronograph does. You have a very bright star, and you wish to see a much dimmer planet. So what do? You block the starlight so that you can see the planet signature. Dead simple, right? In practice, it's a little bit more complex. Here is a video out of Goddard walking you through a slightly one more level deeper view of that. We paid for the production value of this, so I might as well show you.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
Just the focus on the Jupiter. Okay, so that's sort of a general audience picture of what a coronagraph is, but we're all optics people, so let's talk through at an optics level, general optics level, what each part of the coronagraph does. So from the observatory, you come in and the first thing you hit is the fast steering mirror. This is your control of bore sight, so it feeds back and controls tip tilt. It then goes through a relay wherein there is a focus control mechanism which controls focus. And then it goes through 2 deformable mirrors, one in a pupil plane to correct for phase, one slightly off of the pupil plane to correct for field amplitude. And those are responsible for nulling the star and also for maintaining the sort of exotic aberrations like astigmatism and trefoil up to Z11. From there, it goes through into a pupil plane where we put the shaped pupil masks. Shaped pupil masks in the narrow field of view, the primary view, operating mode of the instrument, are just open. They don't do anything. But in the shaped pupil coronography modes, what they're doing is they're applying a windowing function to your pupil so that when Fourier transforms, it does a beneficial thing in the imaging plane. And you'll see a picture of that in a bit. Then it goes through the focal plane mask, which is the thing that actually occults the starlight. And by the way, up here, all of these AMs are alignment mechanism. These are all the 2D stages. So that's shaped pupil alignment mechanism, focal plane alignment mechanism, and so forth. And then it goes through the Leo stop, which is responsible essentially for cleaning up all the diffractive noise in the pupil. Then it goes through a field stop, which essentially is responsible for cleaning up all the diffractive noise in your imaging field. Goes through some color filters because the entire system is extremely chromatic, so we often want to cut down the throughput to a particular band. And then finally, it goes through sort of a grab bag optics stage on the dispersion and polarization mechanism, which has a series of lenses to give you a pupil image or a direct star image, or to give you, there's 2 Wollaston prisms there to interrogate polarization, and dispersive prisms to interrogate spectrum. Finally, that lands on the science camera, the exoplanet exploration camera, I don't remember, XCAM, that gives you your dark hole, your science data, and it feeds back into the high order wavefront sensing and control system that goes to the DMs to control the high orders corrections. The rejected light from the focal plane mask, the thing that occults the starlight, feeds into the LOFIS, the low order wavefront sensing and control system, and that drives the actuators for tip, tilt, focus, and so forth. So this is a shot of all of the different modes of CGI. And we are a tech demo, so we only really use these 2. We included a whole bunch because one of the things that we really wanted to focus on with the CGI project specifically is collaboration with the scientific community. So they brought us mask design and we said, okay, let's put it on. We might not have time to characterize and use it, but we'll at least include it so that we can have it there. And if we just happen to get an extended mission or time on orbit, then we can use those to try and do some science. But we mostly use the hybrid LEO mode, that's the primary operation of the instrument, and the shaped pupil mode. And we also calibrated the shaped pupil wide field, shaped pupil spec, so that we could hopefully do some spectroscopy on orbit. So you've got your chronograph and you want to do things with it. You're going to face, I've lumped these in, well, you're going to face a lot of challenges. I've lumped these into 3 major challenges. And the first one is you have to align the thing. Now, there is aligning a system, and then there is aligning a system. When you go to do the second one for the chronograph, for CGI specifically, you're going to find out that you have 2 DIVA systems for alignment. And one is the LOFIS optical bench element, or lobe, which is the optics that collect the rejected starlight and direct it to the LOFIS camera. The other are your 2 DMs. So for the first one, due to manufacturing and design, problems. The lobe has very bad aberrations in it. And what we found out is that if you are even slightly off the nominal bore side of lobe, then your pupil image just starts to walk off on a fun little adventure somewhere. And to a stray light baffle or the body of the detector, who knows? It's just off on a fun little jaunt. You really want to be within about a 400 milliarc second window to do anything valuable with LOFs. And this led to what we will call a novel alignment technique, where in order to sight your alignment through lobe, you can literally just scan the pupil image through the field of view and track it, and you will know exactly when you are at the optimal bore sight through lobe. Complicating this, though, is the deformable mirrors. Let me hold on before that. So the deformable mirrors are two 48 by 48 actuator grids. And ideally, you want them to be in control. You want the actuators on them to be in control of the exact same part of the wavefront. So you want an actuator and its sibling to both exert basically the same influence function on the same spatial location in your wavefront. There's a mild amount of debate between the coronagraphers and the modeling team about just how tight this tolerance is, but we tried to get it correct to about tens of microns or so on CGI. And so you can imagine that maybe lobe and maybe the two DM bore sites don't perfectly agree to 400 milliseconds or 400 milliarc seconds and 10 microns. So it's sort of a trade of not pissing off either of your divas too much. How do you know what your DM alignment is? So this is a good time to introduce phase retrieval. So for those of you who know what phase retrieval is, this text box is the interesting thing. CGI uses a modified Gertzberg-Saxton algorithm where we use Gertzberg-Saxton in the pupil image and the slightly defocused pupil, and we use simple parametric fitting for the star image and the slightly defocused star image. We marry those two to a total understanding of our wavefront. For those of you who have never seen wavefront or phase retrieval before, phase retrieval is a technique that was pioneered back on Hubble because Hubble famously had a prescription problem and returned a bunch of blurry images, and that was not good. Essentially what you do is you scan through focus on your camera from your pupil to your in-focus image. And then ideally you scan a little bit farther to get some symmetry to your system, but we're limited by discrete elements that you'll see later, so we do pupil to star image. And you can track how that pupil image focuses down, feed it into a model, and retrieve the wavefront that you're dealing with. And so for the DMs, we do this to flatten the DMs because you want to start from flat. And we also do this to measure the alignment. So you put a poke pattern grid to certain actuators on DM1, you do the same on DM2, you compare their overlap, and hopefully they are right on top of each other. Again, we use this to flatten the DMs as well, so your system doesn't start flat, of course. So you measure you measure your wavefront using phase retrieval, you apply a solution to the DMs, you measure it again, and you get to as flat as you can possibly get, which for us was about 15 nanometers RMS across the pupil. That is end to end, and the DMs have trouble handling the stuff past the focal plane mask when it comes to flattening the pupil. So this is actually a very good result. Okay, that's the first challenge, aligning. Second challenge, once you're aligned, is you have your star, and it's gonna not always be in the same spot. This is the plot of the reaction wheels, the expected reaction wheel speeds of the entire observatory through a long period of time. Now, the observation windows for CGI are 10 hours long, and you have to do at least 3. You have to observe a reference star and dig your dark hole. You have to observe a target star where you expect an exoplanet to be, and then you rotate the observatory and do it again so that hopefully you see the planet signature counter-rotate on the image plane. So that is a long time, especially when the reaction wheel speeds indicate that your observatory is doing stuff and you need to keep that star exactly centered on your focal plane mask, or else you're going to ruin the dark hole while you're doing that. So enter LOFUS. So LOFUS, low order wavefront sensing and control, is the system that makes sure the star stays on the focal plane mask and also corrects for the other low order errors like focus and astigmatism and so forth. So the way that LOFUS for CGI works is it collects the rejected light from the focal plane mask and it senses the low orders inside of that. Now, I forget exactly who, but someone deep in the Roman lore once remarked that the Roman pupil is a pupil only a mother could love. And that is extra true for what you get off of the focal plane mask. That's the phase profile of the focal plane mask, and it is nowhere close to flat, which means the pupil image that comes off of that is this eldritch abomination. And you have to somehow sense the morphology of tip, tilt, focus, astigmatism, all the way up to Z11, and properly feed that back into your control system. So this is a modeling results for what those morphologies look like, and if those don't look like the terms that you're used to, yeah. Here are the modeling results versus what we actually measured in TVAC and attempted to measure during our full functional test, which was an error which scrambles everything. The formal ruling of these images is non-quantitative morphological match between model and measured is adequate, but with fine scale differences. That was, quote, Brian Kern, our LOFUS subject matter expert, which I guess means, yeah, it worked. Once you have those, once you have all of your measured modes, then you can construct a vector, feed that into your controller, and it will apply it will apply drive to the relevant actuators and null out what you're seeing. Because your models aren't ever perfect, Roman also intentionally chops the wavefront in order to train the LOFUS estimator before it does that. So you will use your fast steering mirror to intentionally inject Z2, Z3 and measure it to train the estimator on Z2, Z3, use focus control to do Z4, use the DMs to do all the other Zernikeys. And then once you've controlled your star, now you have to null it in order to see the planet signatures. There are a bunch of different ways to do this, and we'll go through each of them. And the first is sort of a classic or hybrid LEO. So the point of the LEO is basically the thing you saw in the video. Either it's a hard binary occulter, or it's one of these phase mask occulters. And where the video said that you phase shift starlight against each other to null the electric field. There's some nuance in there, right? Because if you just straight up null the field, you'd be destroying energy, you wouldn't obey conservation. What is actually happening is you are using interference inside the field of view of your dark hole to shift the energy from those speckles outside of your field of view. And you're either shifting it out in really far out to where it can be cleaned up by the LEO stop, or you're shifting it just outside of your dark hole field of view where it can be blocked by the field stop. And I just love this plot. Is from a Jun Seo paper. You don't often see a dark hole with the bright ring around it because this will very often mess up the actual science that you're trying to do. But Jun included this in one of his papers, which is great. So that's classic or hybrid LEO. The shaped pupil mode, like I said, applies a windowing function in the pupil such that when you Fourier transform it optically onto the focal plane mask, it puts the starlight conveniently in places that are blocked, but the off-axis planet signature conveniently in a space that is passed. And then when you Fourier transform it back into the LEO stop, it does basically the same thing to both, so that when it Fourier transforms back into the image plane on the detector, then you get a nice clear planetary signature. There's also a coronography mode called an optical vortex, either a scalar vortex or a vector vortex. And what these are doing is they are applying in the focal plane a phase ramp or a chopped phase radially like this, such that all of the light from the star centered on the exact center of the vortex winds up in a perfect little circle on your LEO stop so that you can block you can clean all of that up at the LEO stop, and then the off-axis planet, of course, doesn't do that. On CGI, we do not do vortexes. So there's a bunch of other Coronography modes, people mix and match these all the time, and even the coronography mode for habitable worlds isn't set yet. People are proposing a whole lot of different stuff. So there are a lot of options, and a lot of them are very great, except on CGI where you get two. You get hybrid Leo or you get shaped pupil. So those are the ones we included. No vortexes on CGI. So what do you do? What's the process of doing that? So you have an optical model, but it's probably not perfect. So the first thing that you need to do is measure your sensitivities to the way that your DM is controlling the wavefront. So CGI does that by pairwise probing, where you take pairs of actuators and you probe them vertically and laterally. That gives you your sensitivities in your optical control model, which knows all things. The control model is the thing that you rely on to know what the system is doing. It's model-based and then fed in with these sensitivities. It's also very eager. It has big put me in coach energy. And if you just let it run off, it will immediately use all of the stroke available to it to tackle every mode that it thinks needs to be tackled, and it will totally blow up your dark hole solution. So CGI's answer to that is to use Tikhonov regularization, which is essentially scoring all of the control modes that you have access to by how much contrast you get out of them versus how much actuator stroke they use and what their gain multiplier is, or how likely they are to blow up if there's error in your understanding of the system. And it applies sort of an S-curve to that and says you don't have the system doesn't have access to the stuff that's super expensive or that's going to blow up your dark hole, and has full access to the stuff that's nice and easy and gets you a lot of contrast without as much risk. You then apply the solution that the sensitivity or that the control model has given you. You observe your dark hole and you feed that back into doing pairwise probing to assess your field sensitivities again. One of the other things that we do, you do this iteratively, and you do this 60, 70 plus times to dig a really deep dark hole, especially the first time you're commissioning a system. And one of the things that the coronographers on CGI do is they schedule regularizations, which means they schedule iterations where they decide to give the control system access to some of the more spicy modes of the system for one iteration. If you're in the coronography community, you might hear this referred to as beta normalization or beta bumping, or using a beta of -2, -6, whatever. That's because the term in the Tikhonov regularization formula is the beta term, but no one ever explains that to me. Sorry. And you do it this way because, thank you, Brian, the human brain is just not great at handling a 20,000 dimension optimization problem. Okay, and how do you apply the corrections? So this is where my bias shows through. This is my subsystem. This is the deformable mirrors. So the deformable mirrors are these 48 by 48 grids. You have a couple nice CAD shots with the transparent thermal control shroud there and a real photo of it. These are very dense, very complicated, and pour one out for the technicians, very frustrating to work with. To give you an example, the electrical connections on the back side of the mirror are a stacked set of header bars that are 2 by 50. And you have to plug those in very carefully because the pins are very delicate. And then because the front side is sensitive to the force applied to the back side, we had to go through and slightly pull back every other header bar to counteract the pinching force on the back side so that we didn't have horrible, it usually came out as astigmatism on the front side. What are these things? Well, they are based on an electrorestrictive ceramic, lead magnesium niobate or PMN. You make a block of this stuff and you embed metal electrodes inside of it. Then you cut one surface into a grid of actuators and you bond on a fused silica face sheet, which you then we coated with aluminum or protected silver. And then by applying voltage to the pads on the backside, these stubby little guys shrink and fatten out, which gives you local control of your wavefront. All of the modules for CGI were provided by AOX over on the East Coast. Actuators are about 1 millimeter apart from each other. They can move by about 500 nanometers if they are not constrained by the restrictive force of the phase sheet, which is usually how the stroke is talked about. They can move in a 10 to 20 picometer step of resolution, but that's really governed by the control electronics, not necessarily by the response of the actuators themselves. Have about a 1% hysteresis on large actuations. You have to keep these things stable, ideally to sub 1 millikelvin, or the thermal dependence of the gain will start to really eat your performance. They have some detrimental long time constant drifts, and we'll talk about that later. They aren't perfect. What can you do with these? Well, if you're me, you can do quite a bit. There is not much in this presentation that I get to claim is uniquely mine. This slide definitely is. I was in charge of testing the DMs, and I realized at one point that I had control of like a $5 million mirror and no one was watching me do anything, and I handled that with dignity and grace. Okay, so that's how the system works. Let's talk about how we put it together. I'm going to go through this real quick, but if you thought your 502 lab was bad. So you got your bare basic bench, you throw down an alignment interferometer, and you start aligning OAPs because those were the first things that showed up. You go through the final relay of 8 and 7, 6 and 5, those are the one that go through the focal plane mask. Then you have 3 and 4, those translate between the DMs and the shaped pupil mask. Then you have 2, which has a nice little hole in it because you want to be off, or you want to be on axis for the focus control mechanism, and 1 sits behind it, shoots light through the hole in OAP2, off the focus control mechanism, and back to the optical surface of OAP2, which gives a lot of people heartburn. Then we started installing other optics assemblies as they came in. Lobe came in next, and we just used surrogates the whole time, surrogates, CMM, and interferometry to align all of these as we're doing it. This is probably my favorite optic on the entire bench. This is the focus control mechanism, and I love it because that thing looks like a medieval battering ram, and it is a 7-figure cost mirror whose only purpose is to do this. But like really precise. So next up is the shaped pupil, which have that sort of distinctive shape to them. All of the masks are fabricated at MDL, the microdevices lab at JPL. They are made out of black silicon because you need to null the field when it hits. You want nothing to be reflected back into the system or transmitted. Next up are the focal plane mask. This is the phase profile of the actual focal plane mask we use to do hybrid LEO during the TVAC of CGI. And it is God help the person who actually understands why that is the way that we make the focal plane mask, because it is not obvious. Next up is LEO stops. We have the wide field of view, the narrow field of view, and then that bow tie mode for spectroscopy. The 2 DMs are next. These are my babies, of course, with that nice, lovely gold plating and black mat on the front. DM2 went first, DM1 sits on the back. Again, this DM1 sits in a pupil plane, and then DM2 sits off of the pupil plane to correct for different parts of the system performance. Fast steering mirror came in next. This is the entry point to the entire system. Then you have the field stops. Then you have the color filter assembly with all of the different science bands and dark hole digging bands that we use. And finally, the DPAM, or the dispersive and polarization. Here you have your Wollaston prisms and your diffractive prism up top, and then you have all of your lenses for the various stages of phase retrieval, your pupil image and your focus image. And last but not least are the 2 cameras in their lovely, super heavy housings to shield them from radiation when you're out in space. LOCAM went first, and finally XCAM. And then you have your entire system. After we put it together, we of course have to test it. Got to make sure it works before you pay all the money to put it at L2. So we did 1 full functional test, which is a good time. This was just in air. Make sure the whole system, turn it on, command it, make sure it works. And this is a good time to introduce the other thing that I am biased about, which is the simulated star that we used. It's this guy that sits up top of the chronograph and acts as the Roman observatory and the star combined. So the CVS coronagraph verification stimulus with a SimStar. It's ultimately just a supercontinuum laser that we fiber couple and shine light onto a pinhole. And then we use this small little optics bench to condition it as if it were coming through the Roman observatory. So we have a transmissive pupil mask where you put the shadow of the secondary and the struts supporting it. You have a jitter mirror to introduce tip-tilt disturbances as if the observatory were flexing. And then you finally have some alignment mechanisms to make sure you're hitting the right bore site into CGI. This sits above CGI and shoots the laser downward, like the Goldfinger laser from James Bond, which I point out every single time I talk about CVS. Give it a second. There we go. And of course, because I'm biased, I have a bunch of cool pictures of it. This is us installing CVS on top of CGI for the full functional test. On the left side, you see using this yellowish color that's CGI's primary science band. You can see the pupil image and the star image. It's a super continuum source, and you can choose the spectrum you want it to emit, so you can scan it all the way from blue to red. And then two on the right are just some tricks that I caught with my own personal camera. This is an intermediate focal shot of the pupil where you can see a nice Poisson spot in the middle. And this is just some weird thing that happened. It's some weird interplay between an overstopped aperture and my camera shutter. The last two aren't really relevant to CGI, but sometimes you just need to remember that optics is dope and we have dope stuff to play with. After full functional test, we did EMI EMC, which is where you blast the system with electromagnetic radiation and make sure that it doesn't upset any of your controls or telemetry or anything like that. And also you sit there and you record with antennas to make sure that your system isn't going to mess with GPS or downlink or anything similar like that. And you get to work in these lovely, I can't really tell from that picture, but you get to work in these lovely rooms that are all covered with this spiky blue foam, and it feels like an interrogation chamber, which is very fun. After that, of course, there's vibration, because we're going to strap this to a rocket, and we need to make sure it's not going to fall apart. You do 3 axes on sinusoid and random vibe, and I will not subject you to the video again because it's pretty long. And then you put all of this inside of a thermal vac chamber that has a black shroud that you've pumped liquid nitrogen through to get it down to minus God knows what, so that you can simulate being out in the cold of space and operating in those conditions. Shout out here to, it's hard to tell, but this line item right here in the thermal performance for the DM puck being the actual ceramic of 0.2 millikelvin. So some heroic thermal engineer gave us exactly what we wanted and is probably the reason why we have hope that this will perform very well in orbit. Okay, so finally we get to the thing that everyone is actually interested in, which is the performance of the system. So here is a shot of our third attempt at digging a dark hole using hybrid LEO. So you start off pretty bright and you let system control do its thing. You can occasionally see the bright flashes. Those are the beta bumps, the Tikhonov regularization points. And as you dig down, you slowly start to hit a floor, and then you call that we don't have time to continue the test. Our requirement here is generally broken up into coherent light and incoherent light, that being portions of light that you know respond to your control system and portions of light that you know do not respond to your control system. We have separate requirements on those, but if you can get the total contrast below both floors, then you're really solid that you're not misunderstanding coherent light and incoherent light, and you're very confident that you actually achieved the contrast that you're looking for. We seem to floor out into the 10 to the minus 8 realm here, but hold on to that because we actually think we're going to do a whole lot better on orbit for a reason I'll show shortly. This is our third attempt at digging a dark hole with HLC, and that's actually a pretty a statement that we're actually really proud of, because these take a long time. That's 65 iterations, so that's several days to do this. And these TVAC tests, where you got the whole system inside of a thermal chamber, if I am quoting this correctly, can reach 7 figures per day to run the test. So getting any time to continue tests and do more iterations is a big deal. We got through our first couple of dark hole attempts, and we actually went to NASA headquarters and reported the results, and they came back and said, you're allowed to do a third shift. So that was a real big deal for us, that they had the faith in us to go and try and dig even better on our third attempt. We also got permission to do a secondary mode. This is the exact same thing. Previous was hybrid LEO. This is in shaped pupil. One of the things to note here is that this is real roughshod versus the hybrid LEO dark hole digging. And the reason is because we had a grand total of, I think, 3 shifts to do this. And so we did this as quick and dirty as you could possibly do it. We didn't, we did the beta bumping very quickly instead of usually doing a bump and then letting the control system come back and then doing a bump and letting the control system come back. We just tried to dig as fast as we possibly could, and we got that underneath both of our requirement floor. And it doesn't level off because, put simply, we just ran out of time. We didn't have the time and money to test this to the point that we hit whatever floor it will hit. Now let's talk about the performance of LOFs, which is also a thing that is very important, right? How well can you control your star? So the first step of LOFs is to capture the star. Star is not necessarily exactly on the focal plane mask, so you have to go grab it, put it on the exact center of the focal plane mask. The LOFs is not a linear system, especially as you get really far out from the ideal bore site, where it doesn't have a really well-defined estimator. So sometimes it will just sit out there and twirl around a little bit out in the fringes until it finally hits a point that the estimator really well understands and the LOF system really well understands, and then it snaps it into the focal plane. Once it's there, it's then responsible for keeping it there. And so this video, you're going to see, this is tip tilt control. It starts with an injected disturbance from CVS turned on, but the LOF system not turned on, and then it later turns it on, and you'll see it just snap into, there you go, and just sit rock steady where it's supposed to be. So that performance right there is, I believe, sub-milli-arc second. Yes, sub-milli-arc second once the control system's turned on. It also has to do that over a range of frequencies. So we did these, we applied these things called Schroeder signals, which is it's essentially a sine sweep with an amplitude ramp involved, to show that this is LOFs can null out noise in the sub 15 hertz realm, where it's responsible for controlling the star position. Okay, that's all of the great stuff that we learned in TVAC and all of the reasons we have confidence in the system. And here's some of the things that we learned about the system in TVAC and prior. This is the first time I'm going to actually call out the little snarky subtitles that I've been putting in all of these charts. The number 14,392. When the electronics team was delivering the deformable mirror electronics to us, every one of those 3,200 actuators has its own individual drive channel, and they all have high precision resistors on them to the tune of about 14,392 resistors on the DMEs. And after they had delivered the 2 flight DMEs to us, we found out that the lot of parts was slowly going bad. And they had to tear apart both DMEs, unsolder all of the bad resistors, and replace them with higher grade components. So that was our project manager said he will never, ever forget the number 14,392. Okay, yeah, back to the DMs, because I'm me. So we had 2 things that we were mildly surprised about, and one of them hurt us kind of bad during TVAC on the ground. The other one is a little frustrating for on orbit. So the DMs are supposed to set a surface figure and hold it for however long an observation takes. So you at least have to go 10 hours and then the slew and then 10 more hours and then the rotation and then 10 more hours, and possibly longer than that depending on your flux level. First thing we noted was that when you first install a DM in vacuum, you have a convex surface. And then as you watch it over the period of hundreds of hours, that convex surface slowly flattens out and then keeps going into a convex cylinder. And the reason this is happening is because there is those 2x50 headers on the back that control all the electronics connections, and then some reinforcing epoxy to make sure that your pins don't fall off. Both of those things constrict as they lose moisture, and as they constrict, they pinch the back side of the mirror, and as they pinch the back, the front side bows out. That a cylinder optically is focus and astigmatism. That's what these two plots are here, focus and astigmatism. And you can see over the course of about 700 hours with an attempt to make this go faster by elevating the temperature, they just slowly reach some equilibrium value. The equilibrium value was problematic, but we actually managed to null it out and remove the problem through a pretty clever geometric optics technique. If you've ever aligned off-axis parabolas, you know that if you misalign them, you get focus and astigmatism. So if you have bad focus and astigmatism and you cleverly and intentionally misalign a pair of OAPs, you can remove all of the focus and astigmatism from that you already have. And so the INT team heroically did this and took about half of that value out. The problem wasn't necessarily that we weren't going to dig a dark hole, it was that we were railing actuators against the drive, the upper limits of the drive while we did so, which means we couldn't correct for anything else that bad that could have happened. So being able to just cut half of that out and give us a bunch of DM stroke back is a huge deal. This drift is problematic on the ground because, again, you don't want to wait around while you're paying 7 figures a day to run a TVAC chamber. On orbit, it's not a huge deal once you account for the end magnitude by playing the OAP trick, because you've got weeks between launch and commissioning. Your DMs are going to be well dry by the time you're actually using them. The bigger problem on orbit is going to be this. So it's been long known that when you apply voltage to PMN, it will electrorestrict by some percentage, and it will slowly creep the remaining percentage that it will ever electrorestrict by. And the traditional understanding of this is it has to do with the reordering of ferroelectric domains inside the ceramic. So as the small domains of material realign to the electric field, the amount that it has moved also creeps down. That is understood well and modeled well to be a logarithm behavior, and that is not logarithmic. What you're looking at here is the bulk piston of the entire module after applying 40 volts to all the actuators. And it starts creeping and it just keeps going. And the inset here is showing you that it's actually bad because bulk piston wouldn't matter to a coronagraph. Doesn't hit your field sensitivities at all, doesn't ruin your contrast, it's no problem at all. But if you have your actuators in your control map creeping in the same manner, then your control map is shifting. And what this is showing you is that individual actuators are performing the exact same way, proportional to the voltage applied. So your control map is creeping, and this actually did hit the ConOps for Roman. One, in a sort of minor way, we now apply voltage maps that we think we're going to use about 15 days in advance, while the wide field imager is doing its thing. And also in less fun ways, because we have to be very cognizant that you need 5 to 15 days before you use the DMs to do an observation. So second lesson learned that I want to talk about, because I've only got 5 minutes. This is a picture of our color filter assembly, and it is on the Wikipedia article for the entire Roman Observatory. And is there something you notice about this picture? For example, these bright rings from the backlight. It turns out the gaps where that light is coming through are not unidirectional. And the exact same thing happens, and that light winds up inside of your science camera. Here in a pupil image, you can see it sitting on right here on the edge. And this is the thing that we strongly believe was the reason for the 10 to the minus 8 floor in HLC performance during TVAC. This is not going to respond to probing, so it will just sit there and ruin your contrast. This is a very interesting thing to talk about. to optical engineers, because you need to be a little nice to your straight light engineers in this case. We did have engineers who did straight light modeling for the system, and we did also design to have a bunch of baffles installed in the system. And what the straight light engineers looked at was in-field straight light, which is straight light that sort of accompanies the actual beam that you're interested in, and out-of-field straight light, which is straight light that just comes in from all different angles and view factors. And the out-of-field straight light, not so much a concern. The in-field straight light is interesting. There's a baffle like this on all of the primary elements of the system. And as a part of an INT train, another subsystem came to the optics guys and they asked, can we remove the CFAN, the one in front of the color filters? Because it's causing a problem. And the straight light engineers looked at this and said, well, let's be clever in our analysis and let's look at all of the different straight light baffles in our system. And when you do that, you see that the baffle in front of the DPAM, which is downstream of the color filters, blocks everything that the CFAN baffle would have blocked. So if the DPAM baffle is cleaning everything up, no problem. Take the CFAN baffle out. But what they didn't really account for is a very deep nuance of how a coronagraph functions in HLC mode. Remember that you have the bright ring wherein you are throwing all of the energy from your dark field speckles into. Remember that sits right at the edges of the field stop. The field stop's cleaning that up. That means you have a hard edge right where you have a whole bunch of starlight that you have intentionally placed exactly at the edge. So if that sits upstream and you remove this baffle, then you're throwing a bunch of diffractive noise all across your color filters. And some of it is finding a sneak path in the gaps that you can see in the Wikipedia image, and it's bouncing around back there and winding up on the science camera. And it's very interesting that shaped pupil, which does not use a similarly restrictive field stop, doesn't see that problem at all. Because it's a nuanced diffractive effect that relies both on the field stop and the fact that you've constructed this dark ring next to it. So be a little kind to the straight line engineers. The good news is we had always planned to put a CFAM baffle there. So the mountings were already on the bench and the housing for it was already constructed. So we made the baffle mask and we applied it or installed it on the bench and then did an enormous amount of modeling and field of view testing to make sure that we weren't hurting the system by doing this. Modeling of the coronagraph itself, I should probably put a picture of this, and I didn't think about it, shows that if you properly account for this and you intentionally throw some diffractive noise into the coronagraph model, you do see basically this, and if you apply an appropriate stop right where we put the CFAM baffle, it goes away. So we're very confident that this problem is fixed on orbit and that this actually removes that 10⁻⁸ floor for the coronagraph. Okay, this is almost over, I swear. This is the thing that everyone really cares about. We have two requirements on contrast. We have a requirement for the coherent raw contrast, it's 5e⁻⁸, and we have a requirement for incoherent raw contrast, it's 5e⁻⁷. We, in both HLC mode and in SPC mode, got the net contrast below the tighter requirement. So great success, and we are very confident that when we actually get on orbit and give SPC the proper time and give HLC the proper straight light environment, that we'll get far closer to that 10⁻⁹ level that you need to see in ExoJupiter. Okay, that is all, but just before I turn this over for questions, please enjoy these pictures of CGI from inside the thermal chamber that I personally took because it just looks really cool. Okay, thank you very much.
Question.
Yes. So it takes a long time to dig the dark hole. Are you able to use CGI while Roman is conducting its primary mission?
No.
The wide field imaging, or do you have to take over the telescope to do it?
You have to take over the telescope to do it. What we do use the wide field observation time to do is let the DM settle. that control map drift that I showed is proportional to the voltage. So it really hurts when you go from 0 volts up to like 40 volt median, which is where the HLC control usually happens. So if you set it at HLC, the next HLC pattern you want, or the SBC pattern that you want, at the end of your observation, and then let wide field do its thing, it will be nice and well settled by the time the observatory comes back to doing Roman stuff or chronograph stuff. So we do use that time, but you know, to make sure we didn't hurt ourselves.
Any other question? When is it to launch?
2026 at the latest.
And how many years is it supposed to be operation?
I think we have a 5-year primary mission, and between the chronograph actually just sort of limited windows in that because it's not the primary science instrument. I don't remember by percentage how much time Roman or the chronograph gets versus wide field images. So it should be enough to go after some exojupiters to see if we actually can utilize them.
I was wondering about the before and after the vibration test, like if there was any metric to measure how well it stayed after the vibration thing?
Yeah, we sighted in the bore site with an alignment scope and a CNN machine, coordinate measuring machine. And then so we used that. We used those to pin the sort of overall bore site, but then also you can gauge sub parts of the alignment relative to each other. So for example, the DM pair actuator overlap. You have that as a metric for your alignment, and you have the ideal low bore site as a metric for your alignment, and then you have where the star, like what pixel of your camera the star lands on your science camera when you have the other two aligned. And so you can set the system in the ideal bore site for load, and you say, how well do my actuator grids line up? And that gives you an idea of, am I in the same situation I was previously?
And out of curiosity, how well did it do?
There was a minor shift, we suspect, on the vertical axis of DM1 or 2, but it was still well within our bore site requirements. And specifically, even more importantly, we could still make lobe and the DMs happy enough for hopes and lobes to operate. So that's the thing we were going for.
So, do you see hyperelastic behavior on the face sheet of the deformable mirror?
Define hyperelasticity.
So, like in normal like mechanical engineering,
Yeah.
when you're calculating like the finite elements for this kind of stuff, it's all linear. You've got like a linear Hooke's constant.
Yeah.
Whereas that Hooke's constant is no longer linear. It depends on the amount of force and the loads and stress and strain in the material.
It is highly nonlinear. We don't specifically investigate that when we are testing the DMs. What we want to know when we test the DMs is what is our overall stroke, or what is our overall stroke, and what is our stroke per volts at a given voltage, because in addition to the restriction of the phase sheet, you also have the gains of the actuators themselves, which are highly nonlinear. They're shallow at the low and high ends of the drive range, and they're really high in the middle of the drive range. And so we target understanding that and let modeling handle any behaviors of the sheet.
Any other questions?
Right.
What drives the choice of band for the current chronography? You had a narrow band in the earlier slides.
Yeah. I don't remember what drives band 1. Some of the bands are driven by spectroscopy signatures, like they strongly focused on band 4, which is read into like near IR. Why we use band 1 for science, I actually could not tell you off the top of my head. I'm not even going to hypothesize. Yeah, I think that would probably be a question for maybe Ilya, if you wanted to ask why, or Ilya or Vanessa, if you wanted to ask specifically why that's been.
Okay, let's thank Kay